So I'm Nancy Chabot. I'm at the Johns Hopkins Applied Physics Lab, and I'm happy to talk about DART today, the double asteroid redirection test. So next slide, please. So I am a firm believer that you can't talk about DART without starting on September 26th of 2022. And this is the day that humanity first deflected an asteroid. Next slide. So with more than 1 million people watching worldwide, NASA broadcast as the DART spacecraft headed towards a small asteroid that had never been seen before. That's the Mission Operations Center at the Johns Hopkins Applied Physics Lab. And here the small asteroid took shape as the spacecraft autonomously guided itself to hit this asteroid that was 150 meters in diameter that had never been seen before at 14,000 miles per hour. A lot of celebrations to do this moment in order to make this happen. You can see everybody in Mission Operations Center very excited and there that all of this had worked successfully. A lot of congratulations, a lot of celebrations. We had a big party going on at APL at the time, as you can see. Next slide. So while we were celebrating in the Mission Operations Center and at APL, we actually had a CubeSat, a small spacecraft about the size of a suitcase that had been along with the DART spacecraft called LICIACube, the Light Italian CubeSat for imaging of asteroids. It had been kicked off the DART spacecraft 15 days prior to DART's impact, and it flew by and made its closest approach roughly 3 minutes after DART's impact into the small asteroid, and it captured these images. It didn't send them back down in real time. It had to store them on board and then send them back afterwards. And this movie is just looping and it'll go through here again. And as it comes back up through, you can see that there's 2 asteroids here. DART hit the one in the bottom right, and it's got all of this rock and debris and rays of material that was thrown off. And the small spacecraft captured that and then turns as it makes its closest approach and looks back on the system and captures images as it goes on its way. So we're celebrating, but in Italy, they were busy working this whole time. Next slide. This is just one of those images from LICIACube. I feel like the movie is nice to give you a sense of all the images that they captured, but it doesn't show like really the data that's in every single one of those images. So what you have here is just one of those images taken by LICIACube, where the contrast and brightness has been adjusted by a factor of 2 within each of those boxes to really bring out the fine detail and the really intricate structure of the rays. So the DART spacecraft was coming sort of from the upper left-hand corner, and you can see this very wide ejecta, irregular cone of material thrown off. Next slide. But while we're celebrating at APL and they're working in Italy, telescopes around the world were also involved in this campaign. And this shows all of the telescopes that contributed data to those of us on the DART investigation team. On here, there are more than 60 telescopes, and on all 7 continents, literally on all 7 continents, and in space that contributed. So this really was a worldwide effort. Next slide. And this one is a slide that we just made recently because all of the ones on the telescopes on the previous slides were the ones that were actively on the team that shared data. But as you'll see, it was a really spectacular event. And so other telescopes were able to join and publish their data. So this is a map that shows all of the published literature of DART telescopic observations that are out there in the scientific literature since then. And you just can see that this really was a global phenomenon. Telescopes in space, as well as on all of these continents, a whole variety of different sizes, and really just an impressive global contribution. Next slide. And it wasn't just coincidence. Telescopes were always supposed to be a really important part of the DART mission. So DART launched off of the Earth in November of 2021, and there you can see it going on its way as the yellow line. And it's going to the Dimorphos asteroid system, which you can see out there on the light gray orbit. It took a number of months in order to get to where it made that impact in September that I showed you that it started off with. But you can see really clearly from this animation that the timing of DART's impact was not random. It was chosen specifically to be in the fall of 2022 because the distance between Earth and that asteroid system was at a local minimum. It was about 7 million miles away at the time of DART's impact, which is, you know, a safe distance. These asteroids were never on a collision course with the Earth. But as far as the telescopes that already existed on the Earth were concerned, this was a great opportunity to observe this event. And this sort of distance minimizing doesn't happen again for another 40 years. So that's really why the fall of 2022 was the right time in order to do the DART test into the asteroid Dimorphos system. Next slide. So while we're celebrating at APL and Italy's working, telescopes around the world got to work. And the telescopes in Africa were the ones that were positioned to look up at the night sky and capture the moment of DART's impact. And so this is from a telescope in South Africa. And what you see is this, and this is about 15 minutes total for this movie that's being shown here. And you can see an immediate fast plume of material that goes off very rapidly, a clear indication of DART's impact into this asteroid system captured from the ground-based telescopes. So while we're celebrating, while Italy's working, South Africa and other telescopes are putting these images out onto Twitter and social media, and they're circulating around the world, and you know, it's just more work going on constantly. So next slide. About 5 hours post-impact, both Hubble and JWST in space, these space telescopes, turned their sights to look at the Dimorphos system to see the aftermath of DART's impact. In these, the DART spacecraft is coming again from about the upper left-hand corner, striking down into the asteroids, and you can see that wide cone of material that you see both in the Hubble and the JWST images coming off from the side. JWST, if you remember, in 2022 had only recently been commissioned, and this was actually the first time that both Hubble and JWST had looked at the same object at the same time. JWST, actually a lot of credit to that team too, because, you know, they're good at looking at things that are far away. And this was not far away. This was 7 million miles away, and it's moving pretty fast. So they had to do a lot of fast tracking, and they had to really test their system. And the fact that they were willing to do this to capture this really rare and unique opportunity that was the DART test is credit to that team. Next slide. So jumping ahead a little bit, there are so many amazing telescopic images, and I would love to just spend the whole time showing those, honestly. But here we are 2 days post-impact. So by now, a tail has started to form, the same way that you get a cometary tail to form. So again, the spacecraft is coming from the upper left-hand corner, and you can still see the remnants of this really wide, getting more diffuse ejecta cone, but now it's getting strung out into this really long tail of material. And this is captured from a telescope in Chile. Next slide. This is a great animation that we'll just loop through here. And it's basically the first month following DART's impact from the VLT, the Very Large Telescope in Chile. And so you see an immediate brightening of the system, that really large ejecta cone getting pushed on out into a tail as you get through this whole first month of observation. So again, initial impact, brightening of the system, a wide ejecta cone getting pushed out into a tail. Again, this is basically the first 30 days following DART's impact. Next slide. Jumping even further ahead, this is 53 days post-impact. This is from the Lowell Discovery Telescope in Arizona. At this point, the tail is measured to be about 70,000 kilometers long. Our best estimates for the amount of ejecta material is about 10 billion kilograms. And so this is about 1% of the mass of the asteroid or so, we estimate. But you can see, this is why telescopes all around the world were able to contribute to the DART observations, because this is a very popular object to look at. Maybe some of you, you know, had some chances to, and people are really capturing these spectacular images. Next slide. Of course, the telescopes in space often have really unique opportunities, and this is one taken with the Hubble Space Telescope about 84 days post-impact. It's a beautiful image in itself, where you can see the tail extending beyond the frame of the Hubble Space Telescope. But also, what you should look at here is all those little blue dots. And you might see the little blue dots in the background and be like, oh, those are some nice stars. Those are not actually stars. Those are boulders that are 1 to 3 meters in size. So big rocks that have been blasted off this asteroid and have barely escaped the system, but are now floating off on their own as mini bodies of themselves. And there's many of these, over 50 of these boulders that are seen in the Hubble Space Telescope images. Next slide. 169 days post-impact, and you can still see the tail when you stack some images together with good telescopes at Lowell Discovery Telescope in Arizona again. But here we are many months afterwards, and there's still a very clear sign of a tail in these images. Next slide. And here's the last time that we were able to see it. It's nearly 9 months post-impact now, about 280 days post-impact. Hubble Space Telescope stacking many images, but you can see very clearly there's still a clear tail here. And then this is actually when we had to stop our observations. This is the last time that we saw Didymos for a long time because it went on the other side of the sun. If you remember that first movie that I showed you, the geometry of the Earth and Didymos made it so that observations were no longer possible. So this is the last time we saw it, and it still had this tail, and then the observations had to end. Next slide. Observations resumed in sort of the June of 2024, and this is from a telescope in Chile. Now we're 615 days post-impact, so it's been a long time. And there's no sign of a tail. People have taken observations since then, and nobody has seen any signs of a remnant tail. So sometime between then and this, the tail dissipated fully and is no longer visible in any of the telescopic observations that have happened since. I've been told to not be sad that it's over, but be happy that it happened. But I wish we would have been able to see the tail fully dissipate and watch that whole process in action. But we have learned so much from it, and it's been really spectacular. Next slide. So spectacular as the ejecta was, and as cool as all of these telescopic observations were, they weren't really the main purpose of doing the DART test or the real purpose of the telescopes. So why did we crash the DART spacecraft into this asteroid system? So taking a few steps back, let's talk a little bit about this asteroid system. It's a double asteroid system. So there's 2 asteroids here. There's Didymos, which is about 760 meters in diameter. Didymos means Greek, it means twin in Greek. And that's because even when it was discovered in the 1990s with Earth-based telescopes, they knew that it had a companion moonlit asteroid that went around it as well. Now, we got to help name that moonlit asteroid Dimorphos, which is about 150 meters in size. Dimorphos means in Greek having 2 forms. And that's because we knew it would have one form before DART's impact and another form after DART's impact. And so go ahead and click forward 1. So Dimorphos goes around Didymos before DART's impact every 11 hours and 55 minutes. This was known from telescopes on the Earth who had made this observation for decades. 11 hours and 55 minutes, 11 hours and 55 minutes. Like clockwork, very repeatable. So the DART spacecraft came in at 14,000 miles per hour. LiCioCube kicked off 15 days in advance. Spacecraft crashes into Dimorphos. LiCioCube captures those images that I showed before. That impact of the DART spacecraft nudged the asteroid Dimorphos ever so slightly. And so the telescopes got back to work to measure what was the new orbital period. How much had you deflected this asteroid? Because we were deflecting the Dimorphos asteroid around the Didymos asteroid and seeing how effective that was. And from a variety of measurements that were made, it actually changed it by 33 minutes. So it was 11 hours and 22 minutes afterwards. Next slide. And we were able to announce this just 15 days after impact. Really happy when we had the press conference, and the NASA administrator himself said that today NASA confirms that DART successfully changed the targeted asteroid's trajectory. Was super happy to be a part of that moment and to share that success of the mission. We made that measurement in 2 ways, and I'll walk through how we did that next. So next slide. So the first has to do with something that you guys are probably familiar with. It's used with exoplanets a lot. Basically, looking at these brightness curves. And that's as viewed from Earth in the optical telescopes. the Dimorphos system doesn't look like 2 points of light. It just looks like a single point of light. You can't actually see the two asteroids separately. But you can measure the brightness of that system, and that brightness dips slightly when Dimorphos goes through Didymos' shadow. And the brightness also dips slightly if Dimorphos makes a shadow onto Didymos. And so what you see is he's taking this brightness versus time, this light curve measurement, that it has a very regular pattern where you can see these dips in brightness as a function of time related to this rotation period. So this is how they knew originally that it was a double asteroid system. That's why it was named Didymos, because they did this. It was 11 hours and 55 minutes before. And after DART's impact, using the same telescopes, they got back to work, and it was 11 hours and 22 minutes. So this change of 33 minutes. Next slide. We also did it, though, with radar. So we were able to use the Goldstone planetary radar as well as the Green Bank one in coordination in order to make these next observations. Next slide. So what you're seeing here then are radar images, and radar can get direct determinations of both asteroids. So here's Didymos in these radar images from October of 2022 in the yellow square. And you can get direct data from Dimorphos. So Dimorphos is shown there in the green circle in these. And so unlike the optical, you get data from both of them distinctly, and you can get their positions. Now, the position of Dimorphos after DART's impact, if DART hadn't impacted or hadn't changed anything, should have been where that blue circle was. And so the fact that it was where the green circle is rather than the blue circle is also corresponds to a change of 33 minutes. So it was these two completely distinct and independent measurements, the light curves with the brightness versus time, as well as the radar. And they both gave exactly the same response, that we had changed it by 33 minutes. Next slide. All right, so what does this mean? Why do we have to do that? What does this all do? So you might think like this is just physics, we would know what would happen, but asteroids are actually kind of complicated. They're not just sitting there with nothing happening to them. You know, if you just crashed a spacecraft in and there was no ejecta, go ahead and click forward one. You can go next. Yeah, this would be a momentum enhancement factor of 1. Basically, the momentum that you bring in is how much you wind up pushing the asteroid. Nobody thought that was going to happen. Everybody thought there would be some ejecta. The question was like, how much ejecta, and how much would that additionally deflect the asteroid? So go ahead and click again. Next slide. And what we found when we put this all together is that the DART momentum enhancement factor was actually more like 2. That means that the ejecta is like a recoil effect. It's the momentum that you're bringing in with the spacecraft, and then you're getting just twice as much of that as well from the ejecta, and it's recoiling, and it's helping you deflect this asteroid. So to put this into context, this is the sort of thing that if you had an asteroid that was headed towards the Earth, you might want to change that asteroid's course. And this is why you did something that's called a kinetic impactor, crashing a spacecraft into an asteroid in order to deflect its future path. It's the sort of thing that you would want to do years in advance, 5, 10, 15, 20 years in advance, because we didn't destroy the asteroid. We didn't blow it into a lot of pieces. We did make a lot of ejecta, and we did move it, and we did change its future path, but ever so slightly. It was like a small nudge that if you do early enough adds up to a bigger change in its position with time. And the idea would be doing this many years in advance, such that the Earth and the asteroid wouldn't be in the same place in the future. Next slide. And so after we measured how much we had deflected the asteroid, what that momentum enhancement factor was, we got to trying to study what does that mean for this specific asteroid, because we don't want to just apply it to this asteroid. We want to potentially apply it to any asteroid that we need to in the future. So we have to understand the impact itself, so we would know how we could apply it to asteroids more generally if the need should arise. So this is just a nice animation that uses the topography that we got from the asteroid, from those approach images that I started off the talk with, the actual spacecraft model, the geometry that it crashed into there, and the scale of everything. Next slide. And this is sort of the Dimorphos then that you take and you put into your numerical code model. Next slide. And you can see the DART hit right in between these two boulders. Boulders are named after percussion instruments, actually, as it turns out, is the official naming convention. So I think that's because DART, made a big bang into this asteroid, and the IAU, I guess, sometimes has a sense of humor too. Not always, but anyways, that's Adebakke and Baudron, if you're curious what the boulder names are. So which are drums in various different cultures and languages. Next slide. So then this is taking that model that you've set up based on the real data and reconstructing DART's impact event into it. And you can see a lot of similarities here with that wide initial ejecta cone. And you also see that you're not just getting a uniform cone of material. Go ahead and go next slide. You can see it's very similar here. If I stop that animation at a slide that's similar to sort of the Lichia cube, where we were seeing those streamers and those rays of ejecta. Our modeling suggests that that's all due to the specific boulders and the specific topography of the surface. That's why it doesn't just look like a uniform cone of material. It's because the surface is not uniform. The surface has rocks and different things on it, and we're able to reconstruct those pretty well in our models, which is great because, again, the point is not just to understand Dimorphos, it's to understand more generally how you would apply this to other asteroids in the future. Next slide. This is another model here that was done with DART's impact. And it does sort of suggest that the asteroid was pretty weak, is what this model and other models are showing us, that it's kind of what we call a rubble pile. So just a collection of loosely held together rocks, which kind of makes my head hurt when I just think about it, that an object can be so weak in space. But you shouldn't think of it as like cement or a single rock, just all these pebbles kind of piled together and barely held together. Next slide. And the model here actually suggests that if you're looking down at the asteroid before DART's impact, the shape of it was more like that blue circle. And the shape after the impact has been changed by almost 30%, where you're missing that part of the asteroid. Partially because we ejected it, partially because parts of the asteroid are getting compressed, partially because it's on the other side. But the light curves also hint at this and are suggestive that this asteroid, we might have changed its equatorial radius equatorial diameter by about 30%. Next slide. All right, so here also is something, if you just like hit into an asteroid, it was, all happy. Dimorphos was very happy going around Didymos. Didymos has a rotation period, the big asteroid, of 2.26 hours. And Dimorphos had its X, Y, and Z axes, as are shown by those little blue lines that are coming out of Dimorphos. And so this was before, and then go ahead and hit next. All right, and then we think afterwards, so this is sped up, obviously. So Dimorphos really is rotating every 2.26 hours, and Didymos is rotating every 2.26 hours. But you can see the point is the X, Y, and Z axes of Dimorphos are no longer like tidally locked, where we thought prior to DART's impact, the same side of Dimorphos always faced Didymos, sort of like our moon does for the Earth. But that's no longer the case because of DART's impact. Instead, the prediction is that we've put Dimorphos into a tumbling state because of the impact event and the energetics associated with it. So next slide. I've shown a lot of results here. I just wanted to take a moment to acknowledge the team. The DART investigation team had over 300 people on it, representing 29 different countries and more than 100 different institutions. It was really a joy and a pleasure to work on such an international team with everybody contributing towards this. It's not just the telescopes, but these models and everything else that I've shown you has been the work of state-of-the-art facilities and techniques across the world, really. Next slide. But to take a step back, I think it's natural then to ask, like, do we really need something like DART? Did we need to do something like this? Do we need it in the future? And this is a figure that's updated regularly from the JPL CNEOS websites. And it's just the fireballs that are reported by US government sensors going back for multiple decades at this point. And you can see it was just updated September 13th of this year. And that's because Earth is hit by stuff all of the time. Now, a lot of it, is not very big. That's no concern. But you can see this is something that happens. And maybe a lot of people remember Chelyabinsk. That was in 2013. It was about 20 meters in diameter. And it was the one with that went through Russia and hit into a lake. And the fireballs were captured on the dashboard cam. It's the biggest one that's hit during the time here. Clearly that big red dot on this diagram. But we are hit by things all of the time. Next slide. So how many things are we hit by all of the time? So there's something starting over with that 4 meter size. Something about 4 meters hits about once per year. Now, this is really not a concern. In fact, I love these things that are about 4 meters in size and hit once per year because I study meteorites, which are rocks from space. They're free samples from space. Please bring more meteorites so I can have more rocks from space. These really are not a danger, and they can make fireballs. People are capturing them there, but this is not a concern for the field of planetary defense, which is to protect our planet from naturally cosmic impactors. Next slide. So something like 25 meters. This is getting to the size of Chelyabinsk, okay, which was 20 meters. Something like that's about a century, every 100 years or so. If this is over a populated area, it could be concerning. So Chelyabinsk, there were no fatalities, but more than 1,000 people were injured. Mostly by running to windows and then the windows exploding and everybody getting cut up by glass. So you would want to have some warning. For example, if you knew one of these were coming, you would tell everybody not to go run to the windows, which is a very natural thing to do if there's a giant fireball in the sky. I'm just saying, I would probably want to go see what it was. You would just, you could warn people about them. But again, there were no fatalities, so that's not the most pressing priority for planetary defense, things that are about 25 meters in size. Next slide. All right, 10 kilometers. When people think of asteroids, they think of dinosaurs, and that's about 10 kilometers, the size that killed the dinosaurs. Yes, this would be devastating. This would be a global extinction event. This would be a very major and real concern. This does not happen very often, about every 100 million years, but it would be an extinction level event. The good news is that in the near-Earth object space, where the asteroids can come and hit the Earth, there are 4 of these objects. We have found 100% of them, and none are a danger to hit the Earth for the foreseeable future, which means the next 100+ years. So while that is the stuff that you would be concerned about, we have a good handle on those, and they're not a threat to hit the Earth. Next. Okay, so 1 kilometer. 1 kilometers, again, are pretty rare, about every 500,000 years. And 1 kilometer is about where you start to get the extinction level events. 1 kilometer is when it would be big enough to potentially affect the climate, for example. And that's where you can have global consequences as compared to regional consequences when you start to affect the climate. So this would be a big concern as well, these 1 kilometer size objects. But again, good news here is that there's about 900 of them. We've found 95% of them. And of those 95%, none are a threat to hit the Earth for the next 100+ years. So this is also not the priority for planetary defense. Next slide. So that brings us to something 140 meters, which is about the size of Dimorphos, which was 150 meters. And these are also pretty rare, every 20,000 years. But these are the sort of things where they could be regionally devastating. It wouldn't be the end of humanity, but it could be big enough to wipe out a small state, a small country, devastating over a heavily populated area. And so this is really a priority to understand where these are and to be able to do something about them if you needed to. There are about 25,000 of them or so in the near-Earth object space. And we have found less than half of them so far. So sitting there at about 42%. Of the ones we found, none are a threat to hit the Earth for the foreseeable future, but we actually don't know where more than 50% of this population is. So there's a lot more of these objects. They hit a lot more often. So along with trying to figure out where they all are so we could have the warning time, it makes sense to be developing the technologies to be able to do something about objects this size, like Dimorphos, if we needed to. Next slide. And just to put it in a little bit of context, maybe some of you have been to Barringer Crater in Arizona. It's really close to the Grand Canyon. Highly recommended if you're out there and have the opportunity. They have a great visitor center. The crater itself is really well preserved. It formed about 50,000 years ago by a 50-meter object that was mostly metallic, so a pretty dense 50-meter object. It has a beautiful crater there that's about 1 kilometer in diameter, and you can walk out along the rim and see it. And you'll think like this is a cool looking crater, but the point with any of these impacts is that it's so much bigger than just the crater that you see there now. Modeling for this impact event shows that you would have had a fireball that extended out for 10 kilometers from this 1 kilometer crater, that large animals would have been killed or wounded out to 24 kilometers, that you would have had hurricane force winds out to 40 kilometers. And this is from a 50-meter size metallic object. Next slide. So go ahead and hit it again. Putting it a little clearer and dearer to our hearts, you know, where we all are, or a lot of us are and live and there, you know, if you were unlucky enough that it did hit over a heavily populated area, you could see how devastating regionally something like this still would be, even though this is only a 50-meter size object that we're talking about at this point, and just the devastation that it would cause. Next slide. Which brings us back to planetary defense and what we can do about these things. And I've been talking a lot about DART, but it's really important to talk about that planetary defense is so much more than that, to have a strategy and to have a unified approach. You can't do anything about the asteroids if you don't know where they are. So the cornerstone of planetary defense is to search, detect, and track. Find those asteroids. Characterize them. What are you dealing with? What are they made of? Are they double asteroids or single asteroids that you're dealing with? Plan and coordinate. There's actually UN-sanctioned committees that meet on this internationally in order to have the International Asteroid Warning Network and the Space Mission Planning Advisory Group. Mitigate. So that's where DART comes in. We also have done FEMA exercise, tabletop exercises for disaster preparedness, just as you would for other disasters. And then you're constantly assessing the situation, constantly finding the new asteroids, bringing them into the system, making sure that you understand any of the immediate threats. This all seems very logical, but it's a pretty new field, actually. NASA only stood up its Planetary Defense Coordination Office in 2016, and since then, a lot of their activities have been increasing as well. Next slide. Next slide. And it's not just NASA. Oh, sorry, back. I didn't know that was going to play automatically. Yeah, it's not just NASA. It's actually multiple agencies in the United States that have a national preparedness strategy and action plan. And I won't walk through all of this, but you can see a whole lot of acronyms down at the bottom of this slide for a whole variety of government agencies that have contributed to there. DART falls squarely into the reconnaissance, deflection, and disruption missions. But you can see that there's also detecting and tracking, modeling. I'm really happy to see goal 4, which is increased international cooperation, because this is an international issue. We are all on this planet here together. Like you saw, these things hit everywhere. So it's great to see that there. And then strengthening the exercise and impact emergency procedures and enhancing the interagency collaboration is all part of our national strategy here in the United States. Next slide. And it's not just here in the United States. It really is international cooperation for this international issue. So DART intercepted an impact into Dimorphos in 2022, but I'm really happy to share that there's an ESA mission called Hera, and it is going to rendezvous, orbit the Dimorphos system starting in late 2026, so just next year. This is really exciting because we can then see if we have changed the shape of Dimorphos by 30%. Like I was telling you about, seeing if it's tumbling. We'll be able to directly get the mass of Dimorphos, which is something that's really important for understanding the deflection even better, and so more. And we've been always working very closely together, the DART and the Hera teams, throughout both of these projects. Next slide. And Hera is well on its way. Had a beautiful launch in October of 2024. I was down there and able to be there for that launch. And it's just past the 1-year mark there. It had a good Mars flyby. So they are doing excellent in space and on their way to orbit the Dimorphos system in late 2026, late next year. Next slide. And it's not just ESA, the European Space Agency, and NASA. There's actually a lot that's going on internationally for other missions as well. So just to kind of run through, what are some of these other activities that are coming up in the future? I just talked about Hera, which is on its way to rendezvous in 2026. The Japanese Space Agency, JAXA, has an extended mission of Hayabusa 2, which they call Hayabusa 2 Sharp. It has a flyby of a 500-meter asteroid, Torifune, in 2026. And then it's going to rendezvous with a really small asteroid. On here, it says 30 meters in 10 minutes, but actually further work recently published, and I should update this slide, shows that it might only be about 15 meters, and it might be rotating with a 5-minute spin period. So this just makes my mind buzz too. It's this tiny, tiny asteroid, but this is important for planetary defense. We've never been to anything that small, and it's going to orbit an object that's 15 meters in size. The Chinese Space Agency is looking to do something similar to DART, but with 2 spacecraft, because they're not planning to use the telescopes on Earth like we did. If you just crash DART into an asteroid, you wouldn't be able to know how much you deflected it unless you had a second spacecraft there, or if you used telescopes like we did. So they're planning to have a second observer spacecraft there. So they'll have an observer spacecraft around the asteroid, and then have another spacecraft that comes in like DART and impacts it and see what happens. This is interesting because the asteroid that they are targeting currently is about 30 meters in size. So Dimorphos was about 150 meters in size. And the spacecraft was going at 14,000 miles per hour, weighed about 500 kilograms. Models after DART's impact suggest that the DART impact would have disrupted Dimorphos if it was about 80 meters inside. And when I mean disrupt, I mean break into multiple pieces, not just a tail of ejecta where the main mass of the asteroid is still there. I mean multiple asteroid broken into multiple pieces. So doing something similar to something that's 30 meters in size, there is a very real possibility that this will not be an asteroid deflection mission. This will be an asteroid disruption mission, which is interesting in itself. NASA's next planetary defense mission is called NEO-Surveyor, and this is going to find all the asteroids. So this has been a priority for planetary defense for a very long time. It's on track to launch in 2027. And it's a space-based IR telescope that will find more than 90% of the population of 140-meter asteroids and larger. So this is that important part of the planetary defense strategy, that you can't do anything about the asteroids if you don't know where they are. And then there's Apophis, which maybe some of you have heard of. But it's going to make a close approach to the Earth, this asteroid, in 2029. NASA's got the OSIRIS-APEX spacecraft scheduled to rendezvous with it. ESA's looking at a spacecraft called Ramses. JAXA, the Japanese Space Agency, is looking at one called Destiny Plus. This is a really great opportunity. Next slide. Because Apophis is going to fly pass close enough to the Earth, about a 330-meter asteroid, that it's within the geostationary satellites. And it happens on a Friday the 13th. In 2029. It's actually going to be bright enough that you can see it as a naked eye object, if the skies permit, of course, in Europe, Asia, and parts of Africa. So there's like those parts of the world we'll be able to look up. It's going to be sort of the brightness of some of the dimmest stars in the Little Dipper. So yeah, just really there on there. And if you for a while too, if you type 2029 into like your your browser, you get like a whole bunch of Apophis stuff that comes up. Yeah, it's a big deal. Next slide. And people are recognizing it's a big deal. It actually recently, the United Nations just officially announced the International Year of Asteroid Awareness and Planetary Defense in 2029 to take advantage of the close approach Apophis and raise global awareness about asteroids. So it is officially 2029, the year of asteroid awareness because of Apophis. So if you haven't heard about it before, you're just going to hear more and more about it. And it will be a great astronomical object to be able to witness like that. Next slide. So staying on current topics and talking about the future of planetary defense, I've talked a little bit about, when we pick these asteroids, we pick Dimorphos, we pick, we're going to send things purposefully to Apophis. We're picking these other targets. Even China's picking a small asteroid to go blow it up. But there's a saying in planetary defense that you don't pick the asteroid picks you. Because at the end of the day, when you're really dealing with this challenge, you will not have the luxury of choosing which object is getting thrown at you. So you have to be ready for whatever might happen. We had a good example of this recently, and some of you might remember this. And this was a view of the asteroid 2024 YR4. So it was first reported in December of 2024. No big deal. At this point, more than 300 asteroids had already been found this year. Asteroids are found literally all of the time. There was really nothing special about this asteroid. Next slide. People kept looking at it though, and by a month later, in late January, its probability of hitting the Earth in 2032 had risen to 1%. Now, 1% is the internationally recognized threshold for the International Asteroid Warning Network, that UN committee that I told you about earlier, for warning people that, hey, an asteroid impact might be happening. So this warning went out that you might get hit by an asteroid in 2032. At this point, we weren't sure what the size was. There was a lot of uncertainty with it. The size was somewhere between 50 and 150 meters was the best estimate. Next slide. So telescopes kept looking because, this doesn't happen very often that something rises to this. And when they got more data, the impact probability actually increased up to 2%. So then people started to notice even more when you got up to there. And so more observations happened. Next slide. And then in February, it got up to 3.1%, for this impact that might happen just 8 years later in 2032. And there got to be a lot of concern about this. Next slide. But with additional observations, the probability fell all the way back down to 0 just a few days later, and the crisis was averted. JWST has since looked at this object, and it's about 60 meters in size. It actually still has about a 4% chance that it might hit the moon in 2032. We can't look at this asteroid anymore right now because, again, it's gone on to the other side of the sun and is not accessible to any of the resources that we have, but people are still keeping an eye on it. It was a great way to exercise the International Asteroid Warning Network, though. There was a lot of cooperation internationally to observe this object, to get information about it. But it also sort of points out that while DART was successful, there's still a lot that we need to do to increase our preparedness. Because if this had been coming towards the Earth in 2032, there's really not a whole lot that we would be prepared to do about it currently. Next slide. Which brings us back to that we can do things about things because humans are good at doing that. And DART was a great example of, taking those first steps to be able to protect our planet from cosmic impactors. But I always kind of like to return to this too, because fundamentally everything that we do is a human endeavor. This is people who make this happen, people who make space mission happen. And this is when the spacecraft first started to come together in May of 2020. So you just take a moment in your head and try to remember where you were in May of 2020. This is the time when we were all becoming more isolated from each other, when COVID was we realized this was not just going to be a short-lived passing thing even, that we might be here for quite a long while, sitting on our own, becoming more isolated from each other. I know, though, that me and the other people on the team while we were operating safely and putting this spacecraft together with health and in mind, it was really meaningful to be working on something that did require more people, that required us working together, required us to come together, to be future looking, to try to make something positive happen. Next slide. So this is just the spacecraft coming together in September 2020. It started to take on its boxy form, becoming what we see it here today. Next slide. And we did a lot of thermal vac testing. Just sort of have to show these pictures because there was so much effort that goes into this. Over 1,000 people worked on this mission in order to make it happen and make all this come together. Next slide. Here's the rollout solar arrays, which for a company that was in California, they're actually about a school bus each in length, 18 meters tip to tip. They roll out like aluminum foil roll in your kitchen. Next slide. A picture of the imager that took those pictures that started off that movie that I showed you to start with. It's similar to the camera that took pictures of Pluto from the New Horizons spacecraft built at APL as well. Next slide. Lichia cube. This is why I think of it as a briefcase sized, I think, because literally when you put it on the spacecraft, there is a little handle on it for a while. So you like pick it up and you just shove it right there in its little ejector pod. It made its way across the ocean over to Johns Hopkins Applied Physics Lab and got stuck on there, the mighty little Italian CubeSat that took those spectacular images. Next slide. And this is one of my favorite pictures of DART. It was right before it got shipped off to there. Because you can see that it's a very human-sized spacecraft. It's a human-sized spacecraft that we sent on a mission to move an asteroid. Those are the roll-up solar arrays that you see there on the right-hand side, and Lichia cube is sitting there on the front side. But it's a little mighty spacecraft about the size of a person that went out and moved an asteroid. Next slide. Beautiful launch on a SpaceX Falcon 9 from Vandenberg Space Force Base in November of 2021. Also happy that I was able to witness that launch. Next slide. And so then after launching, just to sort of finish up, the first detection of the Dimorphos system by that Draco camera on board the spacecraft was about 2 months in advance, 61 days, adding a lot of images together. That's the first sign of the Dimorphos system. Next slide. And just to end, talking about one of the major technologies that we needed to make this mission succeed. It's called SmartNav. It's the Small Body Maneuvering Autonomous Real-Time Navigation, because acronyms. So about 4 hours and 5 minutes before DART's impact, we were heading straight towards Dimorphos, the larger asteroid. Nobody had ever seen the smaller asteroid Dimorphos before. And we knew that the spacecraft was going to have to target itself. It was going to have to identify Dimorphos from Dimorphos and then autonomously fire its thrusters and navigate itself in order to hit this small asteroid that had never been seen before while going 6.1 kilometers per second, 14,000 miles per hour. Now, we didn't know what the asteroid looked like, and we knew asteroids could have a lot of different shapes and a lot of different lighting, and all it's got is this optical camera on board. And so there was a lot of testing that went on the ground, and we had a lot of confidence. But this is when SmartNav took over at 4 hours out. And if you look at the center of this frame, you can see there's Dimorphos, and you can see the Dimorphos asteroid, and you can't see Dimorphos at all. And this is where we turned on the autonomous navigation at this point, and had a lot of faith that all of our testing would work. Next slide. And here you are, 73 minutes before DART's impact, just a little more than an hour. And maybe you can see that this is the first time that Dimorphos was detected by SmartNav. So down in the lower right-hand corner from Dimorphos there, you can see Dimorphos, this tiny little dot that's finally there. This is when it's first detected by SmartNav. Next slide. And this is when SmartNav is really confident at 50 minutes out. And it says, yes, I'm going to go and hit that small asteroid rather than that big one. and I know what I'm doing, and I'm going to fire my thrusters, and I can get there. It's only less than an hour before impact at this point, and this has to all happen autonomously. So next slide. And this is that last 5 minutes here where the asteroids are coming into view. The big one, Dimorphos, is on the left. Dimorphos is the one that it's going towards the center. The jittering is because it's autonomously firing its thrusters, trying to stay on target to hit Dimorphos. At 2 minutes out, if the thrusters stop, it's coasting in at this point. Its fate is set. It is just heading straight towards Dimorphos. It's only in the last minute here that you can finally see what this asteroid even looks like. It's sending images back 1 per second, working until the last second, and you have impact. And that's DART. So you can go to the last slide. So it's been a great mission, and looking forward to all the future planetary defense activities that happen after this as well. So thank you very much. Happy to take some questions too.
Thank you very much. We appreciate it. Very interesting. Do we have any questions here in the room first? And we had 2 people come in late, but I appreciate, glad they made it. Any questions here in the room? Yes, sir.
How confident are we that we found all of the 10-kilometer objects?
We're confident in the near Earth object space, right? You know, I mean, there's 10-kilometer objects maybe out in the asteroid belt or further than that, right? But in the near Earth asteroid space, we are confident that we have found all of those. 10 kilometers is very large. And people are always looking at the skies telescopes. There's a lot of survey telescopes out there. There's more coming online. Rubin already has been finding a ton of asteroids. So we feel very confident about that size of objects. Now, comets, that's a story, right? You know, if things like that sneak up on you, but that's very rare, more rare. And planetary defense is sort of a game of probabilities at this point, like any other risk assessment, like any other damage assessment that you would do, right? You build buildings that are strong enough to survive the things that you know. So that's why really for planetary defense, it is sort of these few 100-meter sort of objects that are the priority, because they're the ones that we're most likely to have to deal with. This object, 2024 YR4, is a great example of a 60-meter object. You know, those are going to happen a lot. And so we should be able to try to do something about those first. But there will still be more things to do after that as well.
Okay.
Go
ahead, Rosalito. You need to unmute yourself.
Rosalito?
Thank you, Doc. Doctor, I got a question. Why not use a warhead, chemical or atomic or otherwise, to deflect an asteroid? I can understand the issue of trying to do a direct impact, because all it does is going to blast it into a debris field that's still going to come at the Earth. So, but why not use a warhead to at least deflect it?
Yeah, the question is more, if you don't need to, why would you, right? So if you can do something like a kinetic impactor, which is tested because it is the most mature, right? And it is the least complicated. So if you can just crash something into it and that's enough to deflect it and move it out of the way, then there's no sense to make your problem more complicated than it needs to be. Like you said, keep it deflected so it's whole and you're moving the whole thing so you don't have the debris field still coming at you. Once you find these asteroids, you really do have decades of warning time. And that really is sort of enough in order to do that. Now, if you don't have warning time and you need more energy in order to deflect it that much, then people have looked at potentially using explosive devices in order to make a bigger deflection. Some challenges that you run into are international law, for one, right? Which has all sorts of complications associated with that. And then two, it's this deflection versus disruption. Like you can't just nudge something to deflect it. You have to start worrying about actually disrupting it, making multiple pieces in this non-deterministic sort of way, some of which might come towards the Earth, like you said. So a lot of times when people are looking at these So if you don't need to use an explosive, go with this mature approach where you just crash into there, a small deflection, which leads to a big change in its position with time. If you don't have the warning time, you really might be looking at disruption versus deflection, because how much energy you'd have to put into it to deflect it enough to miss the Earth might also completely disrupt the object. So it gets more complicated. It would be better to find the asteroids and not be in that position. But it is something that people think about. And DART really, I should stress that DART was just the start. It was the first test of one potential technique to deflect asteroids. It was chosen to go first as recommended by the National Academies of Sciences because it was the most mature, because it was the most straightforward, because it was the most simple, because it doesn't violate international law, you know, all of these reasons. But that doesn't mean that, you know, you don't want to have multiple tools in your tool chest for planetary defense going forward. Just to take a slight tangent there. These are impulsive techniques that I've been talking about, like the kinetic impactor or the explosive device, like you brought up. The other option for there is more like slow pull, slow push. So people talk about things that are more like gravity tractor, where the gravity would like tug it off its course. It would have to operate continuously around the asteroid for decades, and it would tug it. Or people like an ion beam deflection, where the ion engines would slowly sort of hit it with the ion engines, and that would like push it ever so slightly on there. So those are really being talked about as well. There really is still a lot of technology to be developed in this area, and I'm hopeful that DART will, part of the legacy of DART will be just the first of developing these technologies.
Thank you very much for the answer.
Yeah.
So what is the next iteration of DART from NASA? Like DART 2, has that been developed?
Well, NASA right now, like the NEO Surveyor is the next major planetary defense mission that they're funding, and that's very important for planetary defense to put that space-based IR telescope up there and find the asteroids so we know what we're dealing with. Other things that have been recommended to do are to, yes, do DART potentially to a smaller object, potentially at a higher speed, though you do have to worry about this disruption deflection threshold. But a high priority also is to develop a spacecraft which can just rapidly recon what you're dealing with. It's sort of like when there's a hurricane, you fly a plane into the eye of the hurricane, so you know what you're dealing with ahead of time, right? So you have that. And 2024 YR4 was a great example because we didn't know the size of the object, right, for a very long time. We weren't sure if it would hit the Earth. We're sure it won't hit the Earth, but we don't know if it'll hit the moon. We don't know if it's a double object or a single object. If you had a spacecraft where you could just go rapidly fly by, ready to launch at like 2024 YR4, you would immediately be able to get its position more accurately. You'd be able to get its size more accurately. You'd know what you're dealing with. And so this is a capability for planetary defense that people also really want to be able to develop, is this reconnaissance, along with the deflection techniques and everything that I've talked about. But I think a lot of things with DART showed you that the more information that you have about the target, the better you can plan your deflection as well. So being able to quickly reconnaissance any potential threatening asteroid. Well, I'm not supposed to say threatening asteroid because the asteroids are inanimate. They're lovely objects. They don't go around threatening us. They might be a hazard to us, but they're not human. They're just trying to coexist out there along with us as well, I suppose. So anyways, hopefully that makes sense. Being able to reconnaissance them quickly is a planetary defense priority for a technology development as well.
Thank you.
Any other, I've got one more in here. Thanks.
So was the impactor completely destroyed, or do you think there's a chunk of it left that's big enough that the next observing craft might be able to see it?
Yeah, that's been something that's debated here, because Hera is going to go there and they're going to orbit, and they have 2 CubeSats as well, and they're going to land on Dimorphos and Dimorphos. They don't have like good lander equipment, but they're going to try to put the spacecrafts down. So they're going to have a lot of time to see if they can see the remnants of the DART spacecraft. So DART's impact was not energetic enough to vaporize or melt the spacecraft. It definitely was a, catastrophic sort of disruption of the spacecraft. Mostly people think it'll be pulverized into small pieces, but if there is anything that maybe has a chance of being big enough to see, it would be those giant solar arrays. because the solar arrays are really giant and had very little mass in them because they were just these thin things that were rolled out. So maybe if there's like a hunk of some of that solar array somewhere, that would be your best chance. But people will look for sure. Probably we won't find anything, but that's the best probability potentially, that maybe parts of the solar array were so flimsy that they somehow survived being pulverized.
Okay, anything else here? Not on here in the classroom. Anybody online have any other questions? But
No one online.
okay, thank you. So we certainly appreciate you taking the time to talk to us, and certainly come back and tell us more. I'm sure this is a very interesting subject to a lot of folks, and obviously it's going to continue to evolve. And I've got your coffee, the Novak coffee cup when we get you in person. But anyway, please come see us sometime. We come out to Sky Meadows. We see a lot of meteors come through the atmosphere, and we can see where some of the little ones. But anyway, we certainly appreciate your time, and thank you very much.
Thank you. I would like to come in person sometime too, since you know, I have a sea star now, so I'll put that there too.
We have a lot of places you can come and use that, or whatever. Anything we can do to help. Enjoy seeing you.